Hello and welcome everyone to the channel CSAI Think Tinker Learn. Today we're diving into the absolute deep end of distributed systems, the anatomy of a meltdown. We have all seen it. A perfectly healthy system suddenly buckles under pressure. Today we're going to look at the most terrifying phenomena in distributed systems, specifically the cache stampede, and exactly how we engineer our way out of it. Don't forget to like, subscribe, and hit that notification bell to stay ahead of the curve. And as always, check out my companion website, bitbytoken.com, for my full suite of foundational and advanced system design guides across software, data, AI, and ML. The link is in the description. And this is the site, bitbytoken.com. These are various disciplines, quick navigation. This is split across fundamentals. Each of the fundamentals further are have database basic, advanced, and expert against them. Then we have a sample solution. Each of these sample solution against are further having a FR functional requirement, non-functional requirements, detailed design available, and then several discussions around what exactly needs to be done on those specific topics, like in this case, Instagram. And then we have several trade-offs also considered here. So please do provide feedback. I want to make this site really as comprehensive and as useful for any system design nerd as much as possible. So your feedback is extremely important. Now coming back to our topic for the day, which is anatomy of a meltdown now, which is particularly for cache stampede. Now first, let's talk about the funnel effect. Um, Imagine you have a system with 99% cache hit rate. If that hits 0% for even just 50 milliseconds, you aren't just dealing with high traffic, you're dealing with a destructive, instantaneous spike. Your database was likely sized for average load, not a 1000x surge. Connection pool exhaust in millisecond. Timeouts cascade, and before you know it, the service is down. That is the definition of a distributed system meltdown. This is the cycle of failure. You have a cache miss, 1000 requests hit the DB simultaneously, and the DB slows down to a 200 millisecond query time. Because the DB is slow, new requests pile up during the 200 millisecond window, and the cycle repeats. Real world triggers, they are everywhere. Cache node restarts, bulk admin invalidation, or even a cold start deployment. Here is a senior tip. You can't buy enough hardware to absorb a synchronized 50 millisecond spike. We have to fix the logic, not just throw more metal at the problem. Fix number one, the distributed mutex lock. The logic is simple. Acquire a distributed lock. Fetch from the DB, populate the cache, and release the lock. The other 99 thread wait in a waiting circle. But here is a huge warning. If the DB query takes 500 milliseconds, all those waiting threads are stalled for 500 milliseconds. To prevent redundant work, always use the double check pattern. Check the cache once, acquire the lock, and then check the cache again before hitting the DB. Fix number two, Singleflight. Instead of network-heavy external locks, Singleflight coalesces requests in memory inside the application process using an in-flight map. It treats the process as a single source of truth for a specific key. One fetch, shared results. But note the scope limitation. Singleflight only works within one application pod. If you have 50 pods spinning up at once, you'll still generate 50 simultaneous database calls. We need to rethink expiry. The problem with standard TTL is that it's a cliff edge. You go from perfectly availability to a complete miss in an instant. Instead, we need to ask a core question. What if expiry was a probability, not a hard wall? This leads us to a XFetch curve, which smooths out the expiration cliff significantly. Fix number three, probabilistic early expiration or XFetch. The logic here is that the TTL takes down the probability of request triggering an early proactive background refresh increases exponentially. Under the hood, this requires storing metadata alongside your cache, specifically how long the last DB query took. This forces the system to pre-warm the cache earlier if the DB is slow. You can tune this behavior using the beta parameter. Fix number 4, Stale-While-Revalidate, or commonly known as SWR. This is about changing the fundamental contract with your user. Instead of waiting for a fresh DB read, return the slightly stale data immediately. Zero waiting. Simultaneously, dispatch a background process to heal the cache. This only works if your business domain can tolerate a little staleness, like a social feed or a product catalog. Never use this for financial ledgers. This brings us to the consistency spectrum and the gap theorem. Understand this. Staleness is not a bug. It is an engineered design choice. Under network partitions, caching system must prioritize availability over strict consistency. Eventual consistency is a liveness guarantee, not a correctness guarantee. Your job as an engineer is to make that eventual window fast enough that the user never notices. Let's look at the three types of inconsistency. First, read your own writes. The user changes something, reloads, and it vanishes. Fix, route those specific reads to the primary DB for a few seconds. Second, monotonic reads. Time seems to go backward due to replica lag. Fix, enforce session stickiness. Third, lost updates. Write-write conflicts. The fix for this is use optimistic concurrency control with versioning. Here's your blueprint for cache and validation strategies. You have simple TTL, write through for consistency, cache aside for flexibility, and event driven via change data capture for decoupling. Each has its place, but event driven is largely considered the gold standard for complex decoupled microservices. In the real world, we use a production grade combined architecture. We layer them. We put a Singleflight gate at the entry, an XFetch gate for the cache expiration, and we use SWR to hide any remaining latency. When you layer these, the herd can roll all it wants. The database won't even notice. This is how you build systems that don't just survive, they thrive. Observability is everything. If you can't see the smoking gun, you can't fix the meltdown. Watch for the hit rate drop, concurrent rebuild spikes, and DB errors combined with cache misses. And for the under the hood fix, add random jitter to your TTLs. A 10% variance ensures that thousands of keys don't all die at the exact same millisecond. When you're stuck, use this trade-off decision framework matrix. Start with the cost of the stale data, then move to the cost of a cache miss. If the DB call is cheap, a Mutex lock is fine. If it is an expensive call, use XFetch. If traffic is spiky and unpredictable, single flight is mandatory. Follow the flow and the right architecture will present itself. To conclude, remember the philosophy of graceful degradation. Any system optimized only for the average case is fragile at the extreme. Our goal is to ensure that under massive unexpected load, the system degrades gracefully rather than catastrophically. Serve stale data over refusing to serve. Serialize expensive work. And always monitor the invisible. What's the most extreme traffic spike you have ever had to handle? Let me know in the comments below. And again, if this deep dive helped you, please like, share, and subscribe. See you in the next one.